Hello, my name is Neil Balogun. I'm talking about quantum mechanics application to nanotools, a video created for the midterm test ME590 for Dr. Underdown. Um, I'll briefly talk about quantum mechanics and then go ahead and look at how some of the applications of quantum mechanics applies to nanotools. So background on quantum mechanics, what are the applications in laser tweezers, application to STMs, and the effects on AFMs as well. So yeah, I start off by talking about wave particle duality. In this case, the particle I'm focusing on is the electrons. The Berkeley has started the question saying if light can act as particles, can electrons act as wave, or can particles act as wave? And so he postulated that if that is the case, the wavelength of such particle would have the format h divided by p. So in this case, h is a Planck constant and p is the momentum of the electron. So if that is the case, which is the case actually, the wave equation for such particles can be defined as exponential of I k times z. K is the wave number, and so you can see there that the wavelength is embedded in the wave number, and the solution to a differential equation of this format is actually that wave equation that I was just highlighting. Um, the differential equation is important because it leads us to the energy conservation equation. So going from the macro world to the nano world. Um, so the Schrodinger equation started out with energy balance. So how do we go from energy balance from the macro world and see what the equivalent would be in the nano world? So we earlier on looked at the kinetic part of this energy balance. So we also represent the potential here as V, and so it's equals to the total energy. If you carefully study this equation, you would see this is a eigenvalue eigenfunction problem. If in linear algebra, or even differential equations. So really it wasn't Einstein, but rather Planck had proposed that the energy at 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 nanoscale would be the frequency multiplied by the Planck constant divided by 2 pi. And so if we're able to rewrite our total energy in this format, where we have now included this quantum mechanical definition, then we would see that we can modify this original energy balance and we will get this time dependent Schrodinger equation. So with this equation, we can predict some of the behaviors of the particles under or within a potential. Yeah, I also say that another way to write the Schrodinger equation is to use the Hamiltonian operator. So if we go down, we'll see that the solution for the SE, which is the Schrodinger equation, gives rise to phenomena such as tunneling. So here, tunneling, we talk about electron tunneling, whereby if E is greater than the potential, then we would have this effect of tunneling. Depending on the value of E, it could tunnel through and the value of E would reduce, or maybe if it's not enough energy, it might not tunnel through. Also, it's important to mention the probability density function, which leads us to being able to predict the position of an electron. So if, say for example, we have the electron at position X, and then a certain time later it's at position, we have this spacing of X plus change in X. We're able to predict where the electron will be between the spacing by using the probability density function. Also, lastly, I point out that it's important to look at the uncertainty principle, which says that it's impossible for us if we know the position exactly. It's impossible for us to know the momentum exactly, or vice versa. So that's the basic review on QM. So what are the applications to laser tweezers? So laser tweezer, quick review is that the principle is that light will exert force on matter, and laser pretty much uses this fundamental principle to be able to trap objects or particles. One of the things I thought I should point out was the quantum mechanical effect, where we are able to define our momentum as the Planck constant divided by 2 pi times the wave number. So with this momentum definition, we can calculate what the change in momentum would be, or what would the momentum delivered to the particle by the laser would be. And we see that it's a function of the energy of the beam divided by the velocity of the wavelength in the medium. We can also look at what the force would be. So the force would be the power of the beam, again divided by the velocity of the beam in the medium. So that's a quantum mechanical effect we see in laser tweezers. Also in STM, so the tunneling effect that we predicted through QM has been used for us to create a scanning tunneling microscope. So again, yeah, I showed the schematics of the scanning tunneling microscope, and you can see where the very tip of the STM is close enough. If it's close enough to the sample, the current tunnels through, or the electron has the ability to tunnel through, and this information is shared on the screen. So rastering through the sample, we're able to generate the image of the sample. Yeah, I quickly show this is from one of the videos Dr. Underdan shared with us. I quickly show the resolution of our STM, saying that if you get the tip as close enough to the sample, you would see that the tunneling current is an exponential function. So it would exponentially degenerate the farther away you put the tip is positioned. So lastly, I talk about the effect of QM on AFMs. So AFMs, again, so it works with the principle of optics and forces, measuring forces from a flexible cantilever. So what I essentially want to bring out here, because my time is running out, is that the forces at the quantum level are greatly emphasized, or greatly the magnitudes are higher at quantum level. So here we have van der Waals force, electrostatic force, magnetic force, capillary forces. So the effect is huge at quantum level, and versus the macro world. So we're able to use that to measure 3D resolution samples, or we're able to generate 3D resolution samples, image of the samples. So finally, yeah, I've been able to quickly review quantum mechanics, talk about some of the effects of QM in laser, STM, and AFMs. Laser uses the principle of light interaction with matter. STM validates the prediction of electron tunneling, and AFM shows some quantum mechanical effects at the tip or the cantilever. Thank you.